It says person A lexicographically prefers good X to good Y. That is, when comparing two bundles of X and Y, she strictly prefers the bundle that has more of good X. If they have equal amount of X, then she strictly prefers the bundle that has more of good Y. Then A's indifference curve are. We actually went ahead and we discussed this in one of our lectures, advanced lectures. So, the same question of lexicographically preferences has, been asked one more time, but there, instead of none of the above, the question given was a convex set. You can refer to my lecture on lexicographic preferences. So the option given was a convex set, and this is what we had marked as the right answer. Let's go ahead and understand why this happened. So what is a lexicographic preference? A lexicographic preference of X over Y is where X is strictly preferred over Y. So it's like saying that, if I have a bundle A, and let's say that this bundle A has 1 unit of good X and 5 units of good Y, and bundle B has 0 unit of good X, but 10,000 units of good Y, then also I will go ahead and prefer A over B. This is what lexicographic preference is. You will always go ahead and prefer the bundle which has more of good X. You will not go ahead and compare what happens to Y, as long as the bundle has more of good X. Now, in case of lexicographic preferences, we do not have indifference curves. All we have are some points, individual points. Each point represents different level of utility. So take an example. For example, let's say that this is a point that I have. This point is point A. This is good X. This is good Y. Now point A has this much units of good X and this much units of good Y. Now consider any point to the right of point A. So consider a point like this, maybe a point, let's say B. Clearly B has more of good X. So we know that B should be preferred over A. Consider a point like point C. C also has more of good X. So C should also be preferred over A. Point D. D also has more of good X. So D should also be preferred over A. Point F. F has same amount of good X. But what is lexicographic preference? That if you have same amount of good X, then whichever has more of good Y. So F has more amount of good Y. So F should be preferred over A. Point, let's say G. G should be less preferred over A. You can take different points, H, I, O. Each point will have different level of utility. You cannot find 2 points which will have the same level of utility. That is what is unique about lexicographic preferences. Each point represents different level of utility. Now, it says, should the indifference curve be vertical line? Now, by definition, indifference curve are those curves which represent same level of utility. If I draw an indifference curve like this, IC1, and let's say I have an indifference curve here, IC2. Supposedly, I take IC1 and I take different points on this indifference curve. Let's take a point A, point B, point C, etc. Now, clearly, all of them have same amount of good X, but C has more of good Y than B. B has more of good Y than A. So since C has more of good Y than B, and B has more of good Y than A, I clearly understand that they should not be lying on the same indifference curve. They do not represent the same level of utility. So I will go ahead and cancel this option. No. Now horizontal lines. Exactly same concept. You can try and apply. So if I have horizontal lines, then supposedly I take this indifference curve. I take a point A. I take a point B. I take a point C. If A, B, and C are on the same indifference curve, it says utility from A should be equal to B, should be equal to A. However, this is not true because C has more of good X than B and B has more of good X than A. So C should be preferred over B, should be preferred over A. So they should not be on the same indifference curve. Again, this eliminates horizontal lines. Diagonal lines. Draw a diagonal line and check. Here only let me draw a diagonal line. Diagonal line would mean that point O and point D has same amount of utility. But that is not true. D has more amount of good X and hence should have been on a different point, different indifference curve. They do not represent the same level of utility. So even this is cancelled. So for the question number 1, my answer is none of the above. Actually, lexicographic preferences are just points. Each point in itself is a convex set. So we can have the answer as point. We can have the answer as convex set, or we can have the answer as none of the above. Okay. Now, go ahead and tell me for the second question, what did you do? What is the answer? Just see this once.
Ma'am, I selected answer option A.
Okay, let's go ahead and check this out. See, it says consider the bundle 2, 1 and a sequence of bundle Sn such that each bundle is strictly preferred 2 to 1. So ideally what is happening is, let's say that I have this bundle 2, 1. And whenever I create a sequence of bundles Sn, whatever the sequence is, this sequence is strictly preferred over 2, 1. Now, what you can go ahead and do is you can, in order to create this 2, 1, you can refer to sequences in series. In order to create this bundle, you can take different values. So for example, you can go ahead and you can say, let the sequence be 1 plus n, comma n for n starting from 1 to infinity. It starts from 1 and it goes till infinity. This can be a sequence. A sequence usually goes ahead and it represents a pattern. For example, 2, 4, 6, 8, 10. This is a sequence. It represents a pattern that I'm adding 2 to it. My other sequence can be, let's say, 2, 2 by 4, and this can be nothing but 1 by 2, or let's say this 3, 9 by 2, let's say 27 by 6, and so on. This is also a sequence. I just created one. Now, what kind of sequence this is? What kind of pattern does this sequence create? Well, this creates a pattern where I'm saying that each element is 3 to the power n upon n factorial. This is the sequence that I just created. How? If I put n equal to 1, I will get 3 to the power 1 upon 1 factorial, which is 3. If I put n equal to 2, I will get 3 to the power 2, which is 9, upon 2 factorial, which is 2. If I put 3, I will get 3 to the power 3 upon 3 factorial. 3 factorial is 6. 3 to the power 3 is 27, and so on. So ideally, for something to be called as a sequence, you must have some pattern that you should be able to see. So for example, if I am seeing here, it says that consider the bundle to 1 and a sequence of bundles Sn such that each bundle Sn is preferred to 1. So, I am saying that whatever sequence I'm creating, whatever patterned sequence I'm creating, whatever bundle you obtain for different values of n, over all those bundle, 2, 1 would be preferred. This is what I'm going ahead and saying. Now, there are 2 ways to go ahead and solve this thing. If you are not given any particular sequence, any particular pattern, then you will try and create a sequence such that you are able to get this bundle 2, 1. So for example, when I put n equal to 1, I will get 2, 1. When I put n equal to 2, I will get 2 plus 1, 3, 2. When I put n equal to 3, I will get 3 plus 1, 4, 3, and so on. And now I am saying that over all these bundles, 3, 2, 4, 3, etc., 2, 1 is preferred because no sequence was given to me, right? But you have to create a sequence first. Then it says if the sequence of bundle converges to a bundle S. Now for this, you must understand what is a converging sequence and a divergent sequence. So again, this is something we covered in maths, but let's understand this. A convergent sequence is one where as limit n tends to infinity for the sequence, you get some number. You should be able to get some number. And a divergent sequence is where a divergent sequence is where limit n tends to infinity, the sequence just gives you infinity. So for example, if I say my sequence of n square, then now as limit n tends to infinity, any sequence of n square will simply give you infinity because you're just saying infinity square. as n keeps on increasing, your number will keep on increasing. So this is a divergent sequence, clearly. But take another example. So for example, let's say that I have a sequence which is n plus 1 upon 2 plus n square. I'm just taking some random example to make you understand what is a convergent and divergent sequence. Now when I will apply limit n tends to infinity, n plus 1 upon 2 plus n square, if you directly apply, you will get infinity by infinity. So usually we don't do that in limits. So what you will do, you will go ahead and you will say dividing both numerator and denominator by n. So you will have n plus 1 by n upon 2 plus n square by n. You will get 1 plus 1 by n upon 2 by n plus. Now, if you go ahead and apply here as limit n tends to infinity, you will go ahead and you will get 1 plus 1 by 0, 1 by infinity upon 2 by infinity plus infinity. This will be 1 plus 0 upon 0 plus infinity, which will be 1 by infinity. Anything 1 by a very large number should go towards 0, but we haven't still got exactly equal to 0. Now take a third case. Suppose this is n, and here also you have n. This becomes 1, and here also you will just have 1. Here you will just have 1. So 1 by infinity is 0, 2 by infinity is 0. So you will get the answer as 1 by 1, which will be 1. So we are saying that as you keep on increasing n, this sequence will converge towards 1. So let's see here. If I go ahead and I put different values, suppose I put n equal to 1, I will get 2 plus 3. If I put n equal to 2, I will get 3 by 4. Then I will get 4 by 5. Then I will get 5 by 6 and so on. But even if you put something very, very large, if you put 100, you will get 101 by 102 and so on. Slowly, 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 you will go towards 1. This is what we are saying. Even when n goes very, very large, the entire sequence will converge towards 1. This is the concept. This is what we are trying to say. This is the convergent sequence. So now, coming back to this question that is given to us. This is a convergent sequence. It converges to S. So now, I will give you a sequence, because if you use this sequence, 1 plus n comma n, this is not a convergent sequence. Now go ahead and take this sequence. So supposedly, I want to take a sequence which has n in the denominator, such that when I apply infinity to it, anything by infinity becomes 0. So I take a sequence, and let's say that this sequence is 2 plus 1 by n, comma 2. Usually you will be given sequence. This will be given to you. What sequence you should take. Don't worry about this. So this sequence, this will be given to you. Now again, try with different values. Put n equal to 1. When you put n equal to 1, you will get 2 plus 1, 3 by 2. This is preferred over 2 by 2, right? This is what it says. Each bundle Sn is strictly preferred over 2, 1. So 3, 2 is preferred over 2, 1. Put n equal to 2. You will get 2 plus 1 by 2, which is 2.5, 2. So this is also preferred over 2, 1. This is given to you. Now let's just check for infinity clearly. So for n equal to infinity, let me just put limit n tends to infinity 2 plus 1 by n comma 2. So this will be 2 plus 1 by infinity comma 2. So this will be 2 plus 0 comma 2, which will be 2 comma 2. So I will get 2 comma 2. And I'm saying this is also preferred over 2 comma 1. This is actually S, the bundle S. This entire sequence of bundle, this is converging to 2 comma 2. This one. Okay. Now, if you go ahead and you notice, then can we just simply say that this is a monotonic preference? This bundle clearly had more of X and Y. So this was preferred over 2 comma 1 and this was given to us. This bundle also had more of XY. So because it had more of XY, it was preferred over 2 comma 1, it was given to us. So from the pattern that is given to us, we understand that our preferences are well-defined preferences. We understand that they are monotonic preferences, that more is preferred. So when more is preferred and this sequence converges to 2 comma 2 and this has more of good Y, this should be preferred over this bundle. So even this converged bundle, the entire sequence converges to this S because this S has more of good Y. And from the pattern, we see monotonic preferences. More is preferred. It should be preferred over 2 comma 1. So we come to the conclusion, and you were correct, that S is preferred to 2 comma 1. But you have to, in the background, understand all of these concepts very well. What is a sequence? What is a convergent sequence? What is a divergent sequence? Why am I saying that it is preferred to 2 comma 1? Is this sequence, every bundle of the sequence, following the property of monotonic preferences, or is it not following that? Okay.